Hi everyone, this is Mrs. Smith, and today I want to talk to you about SI versus US units. We're at the beginning of the year, we have a lot of basics to cover, and this is a great place to start. So, first we need to define what a unit is. When you're describing a quantity, you want to make sure you're referencing what scale that quantity was measured in. So, for example, if I wanted to talk about how far someone lived from my house, I wouldn't just say they live 3 from my house, because you don't know what 3 means. Is that 3 houses down, 3 blocks away, 3 miles away, 3 kilometers? It's very unclear if you just say they live 3 from my house. So, of course, we need to include that unit of measurement after the number 3 so we know what in the world 3 is referencing. And in this case, maybe it is that they live 3 miles from my house. Living in the United States, that is a typical measurement of distance that we use. And so, the unit of measure would be miles in that example. So, whenever we are taking measurements in physics class, or we're referencing problems that include units, we have to make sure we pay close attention to what that unit is, because it provides very important information. Good question here. Do all quantities have units? I want to say yes, they all do. Make sure you're always looking for the units, but that's not true. Most quantities that we deal with in physics will have units. However, there are some quantities that are actually ratios. And when setting up that ratio, the units cancel. And so the value that you're calculating ends up not having units. So let me give you an example here. If we take a look at this first equation over here to the left, and please realize that you are not supposed to know what these mean yet. We're just starting. I'm just throwing up different equations here to get you familiar with the concept of units. So this equation to the left, it's an equation for the coefficient of friction. That's what that crazy looking U thing is. That's actually the Greek letter mu. And it is equivalent to the frictional force divided by the normal force. Okay, since they're both forces, they're measured in the same units, and the units cancel out or become 1. Whichever way you like to think about it, but I guess it doesn't cancel. It becomes 1, the unit there. And you end up without having a unit for that coefficient of friction. The same thing happens here on the right-hand side. Okay, this is an equation for calculating the index of refraction of a material, and it's equal to the speed of light in a vacuum divided by the speed of light in a specific material. Well, since they're both speeds, they have the same units. So again, those units will cancel out, become 1, and your index of refraction ends up not having a unit. So I wanted to show you a couple of the exceptions so you know, okay, most of my numbers are going to have units, but there are going to be these few scenarios where they don't. Now, if you live in the United States, there are typically 2 measurement systems that you use in your life. The first measurement system is the Système International. This is the system that was first adopted in 1795 in France, and slowly kind of spread its way around the world. And then there's the US Customary System. And the US Customary System is the system that is used in the United States only. This is the system that in 1776, the United States had adopted the English system, and then as time evolved, it kind of evolved into this US Customary System that we now use. Okay? So there are 2 different systems right now used in the United States. This is a lovely map, and this map shows you the countries that do not use the metric system, who have not officially adopted the metric system as their primary system of measurement. And as you can see, we have the United States, Liberia, and Myanmar. And Myanmar is actually in the process of metrication, that's transferring to having the metric system as their official measurement system. So that leaves the United States and Liberia. This is something that I go on, and I even have a podcast, the Finding Physics podcast, where you can listen to me rant about this. Why in the world doesn't the United States just adopt the metric system like everybody else has? And but that's for another day. You can listen to my podcast if you want to hear me go on and on about that. So for IB physics, we use the metric system. Okay, do not use the English system. And you may be thinking, well, how do I know which system's which? Let me make it clear to you. Here's the metric system. The metric system, which is the system used all over the world and is also the system that is used primarily, even though it's maybe not mandated, but it is used primarily in the United States for medicine, engineering. The government uses it for measurements. So it is used a lot in the United States. The metric system is set up and it has 7 fundamental units. That's like the backbone of this system. And if you take a look as we go around this little graphic I have here, you can see each of those 7 different fundamental units. So first, we have mass. Mass is measured in kilogram. That is the fundamental unit of mass. Anytime you do measurements, that's the fundamental unit. Length, the fundamental unit of length is meter. Time, the fundamental unit is seconds. For temperature, Kelvin. For electric current, the ampere. For luminous intensity, candela. And for the amount of substance, a mole. And that is the foundation of the metric system. All other units that we deal with in physics are called derived units, and they are a combination of these 7 basic units. Being in the IB program, I can tell you that it has frequently showed up on paper 1, which is all multiple choice, different types of problems to see if you know what the fundamental units are for the metric system. So they'll list a bunch of units and say, hey, which one of these is a fundamental unit, or which one of these is not a fundamental unit, or something like that. So you do want to know what the 7 fundamental units are. And like I said, all other units that we use are just based off of these 7. Okay, so that's our foundation. In the US system, here are some common measurements that are used. So for temperature in the US, we typically use Fahrenheit. For weight, we use pounds. For length, we use a whole bunch of different things. Inch, foot, yard, mile. Times, we still kind of base off the second. And for volume, we have, again, a nice long list: teaspoon, tablespoon, cup, pint, ounce, quart, gallon. So for the US system, the units are completely different than in the metric system. And a lot of people in their home or in their daily life in the United States use this US Customary System. You can see that one of the downfalls of this system, if you look at volume alone, is that there are so many different ways to measure volume, where that's not the case. If we're talking about the metric system, we're talking about the liter for volume. So I need you right now to stop, my little IB physics students here, stop and tell yourself, even though I use some of these US units daily, when I'm in this class, I use the metric system. Okay, that's what we use. So if you mistakenly take a measurement in one of these different things in the US system, you're going to need to convert it to the metric system. Do not hand in a lab report, a PSOW, with units in some US customary system. They all need to be in metric system. Okay. So if you do have a measurement in a US system, how do you convert it? Well, you can use the computer and just look up a conversion system and type it in and get it to spit out to you. That's fine. But sometimes you won't have access to that. So in that case, you might need to use some type of conversion factor. And if you look at the sheet in front of you, I have some typical conversion factors that you may need to use. For example, length. We have a meter is equivalent to 3.281 feet. And if you take a look at the bottom of the sheet here, I wrote that out as a conversion factor. I have 1 meter equals 3.281 feet. So that's what this chart's trying to tell you. Or if you take a look at pressure, we have a Pascal, and over here it has what a Pascal is in PSI. Okay, so I wrote down here another conversion factor. 1 Pascal is equal to 1.450 times 10 to the negative 4 PSI, pounds per square inch. Okay, so we need to use these to help convert from one thing to another. So here are a couple quick examples. Just to remind you, I know you've done this before somewhere in your math or science careers, but just a little friendly reminder of how to use these conversions. And like I said, you'll probably be using them a bit in this class, depending on how you took a measurement or how you looked up a measurement. So let's start here. Let's do maybe 3 examples. What if I measured the width of a room and I found that the width of the room was about 14 and a half feet. 14 and a half feet. And I want to convert that into meters. Okay, so I'll show you a couple different ways to do this. I would often put a little multiplication sign and draw a horizontal line here. If you want to think about it, this 14.5 feet is like it's over 1, if you want to picture it as a fraction. And I want to convert from feet to meters. So I look at the top of the screen and I say, oh, look, I have a conversion. I have a relationship in between feet and meters. And I need to realize how to put this relationship in this fraction. Now, if I want to get rid of feet, do you see over here how feet is in the numerator? In order to cancel feet out, I will need to put feet in the denominator here. So sometimes what I do to start is I just remind myself, hey, I need feet to go in the bottom, and then I need meters on the top. And I go back to my little conversion that I see in the top, and it reminds me 1 meter is equivalent to 3.281 feet. And I can see those feet will cancel out those feet. And then I plug this math into my calculator, and my calculator is going to give me a value of about 4.42 meters. Okay, so we converted from feet to meters there. I will tell you that typically whenever I'm writing down these answers, I'm following my significant figure rules, which are going to be in another lesson for you to look out to. So if my calculator might have a little different number or your calculator reads a little differently, know that I'm trying to round my answer following the significant figure rules. And again, we'll discuss that further later. Here's another one that we could do. What if we were talking about, say, tire pressure? And the tire pressure was about 32 PSI, pounds per square inch, but I'm just going to say PSI, and I want to change that to pascals. Okay, again, look at the top. I have a conversion factor for that. I know how many pascals, or that 1 Pascal is equivalent to so many PSI. So I'm going to use that conversion factor to convert from PSI to pascals. Again, it's like this is over 1. But instead, let me show you another way you could set this up. Maybe instead of doing the multiplication, some people have been taught in the past to kind of make a big horizontal line and make these vertical dividers. It's the same thing as I wrote above, just a different way of looking at it. I want you to find methods that work best for you and that make sense for you. Okay, so if I'm going to change to pascals and I look up here at my little conversion, I can see that since I have PSI in the numerator. If I want that to go away, I need to put it in the denominator here so they can cancel out. So I know that I'm going to want PSI in the denominator and pascals in the numerator. And then I go up here to my conversion and say, okay, that conversion says 1 Pascal, that's a 1, sorry guys, is equal to 1.450, I'm getting sloppy, times 10 to the negative 4. And then I go through, I put that in my calculator, and I can see that the PSIs are going to cancel out. And I get on my calculator that this is about 2.2 times 10 to the 5th pascals, PA for pascals. Okay, so I, right there, converted from PSI to pascals. Let's do one more conversion. Let me see if I can erase this off fairly quickly and get you one last conversion here for practice. And then you will be able to do some of these on your own. Okay, my last one that I want to do, what if we're talking about the speed of a car? And you, for some reason, have the speed of the car in feet per second. Definitely not common. So I'm going to say 40, and I put a little decimal point there. Again, I'll explain that when I'm talking about significant figures, but that this car is moving at 40 feet per second. So I have feet. I'm going to make my big old horizontal line. I don't know if that's too long, but we'll see. Feet per second. And I want to convert feet per second to miles per hour. I know that's still in the US system, but I just want to show you a little conversion here using the conversions that you have in front of you. And I'm going to do this in a silly way. I'm going to pretend that the only reference you have are these 3 conversions up top. Now, obviously, this last one, the Pascal one, is not helpful in this conversion, but I do have a conversion from feet to meters at the beginning, and I have a conversion from meter to miles. So let's pretend that we live in a silly world where all you know are those conversions there. And that's what we need to use to try to get to miles per hour. Okay, so I can get, according to my first conversion, I can get from feet to meters, and then I could use this second conversion to get from meters to miles. So let's do that. So I know that I would need feet on the bottom and meters on the top. So I look at my conversion, 1 meter has 3.281 feet. And that gets me rid of the feet, but now I have meters and I want to get to miles per hour. So now I use that second conversion that gives me the relationship in between meters and miles. So I'm going to put meters on the bottom. So that's going to be 1609.34 meters in 1 mile. And I just used that conversion that was listed right above to get that. Now my meters cancel out for my units. And if you take a quick look where we stand right now, I have miles in the numerator and seconds in the denominator. Now I wanted to get to miles per hour. So I'm not finished yet. I still have to keep going. So I need to go from seconds to hours. Now, some people may know how to go convert from seconds to hours in one swoop. Because this is one of the first times of me doing this, I'll kind of show you step by step. So first I will go from seconds to minutes. I know that there are 60 seconds in a minute. Now, since seconds are in the denominator to start, to cancel them out, I would need to put them in the numerator. So I would say 60 seconds are in 1 minute. And my seconds cancel. Now I have minutes in the denominator. You can see this is taking forever. And this is not really a realistic problem, but one that gives you some practice. One that gives you some practice with doing conversions. Okay, so now I still want to get to miles per hour. I need to change minutes to hours. So I would need minutes to be in the numerator and hours in the denominator. And I know there are 60 minutes in 1 hour. minutes, minutes, and lo and behold, just looking across the top, I have miles. Now in the denominator, I have hours, and I'm going to plug that math into my problem. So I'm going to multiply across the top and divide by everything that's in the bottom. And if I do that at once in my calculator, I have to make sure I have parentheses around my denominator if I'm going to do it in one move. And I end up getting on my calculator about 27 miles per hour, which, by the way, is sometimes written mph, miles per hour, just so you're familiar with it. So we went through, and I know, isn't that kind of a silly problem? That really wouldn't happen in real life, but just trying to give you some examples. But I want to point something out that's helpful for you. Do you see here how it took me 2 steps to go from seconds to hours? It is unlikely that you would take that many steps. Instead, a good conversion for you to be familiar with is that there are 3,600 seconds in 1 hour. We use that conversion enough that it is worth kind of noting that that is something that would be helpful for you. Okay? So 3 examples of doing conversions, some in between US and SI, and this last one just kind of a silly long one for you to get some practice converting. Why are units important in physics class? Well, we need to know what measurement scale is being used for different quantities to make sure we're recording everything with the proper units. If a unit's in one system, you may need to convert it to another system. So if you get something in a US system, this is IB physics, you would need to convert it to the metric system. In the real world, in the United States, we are using both systems. If professionals don't pay close attention to the unit of measure, it could cause catastrophic and fatal errors. And it has happened throughout history that these 2 systems were mistakenly intertwined without proper conversions, and we've had a lot of different issues. So managing the 2 systems, you really have to make sure you keep track of what system you're using and what units are associated with your measurements. Okay, everyone. That's it for now. I'll see you next time.